So in your textbook, they have given some steps, but really there were some gaps. So I went ahead so that we understand the process. It's a similar process to what I had done.
Maybe there is no electricity.
No, there is this one. Oh, there is. No, there is electricity. It's not. Puerto Rico doesn't have electricity, so we are okay. Okay, so we will do this 4.4b. 4.4a is, I have just gone through that. So I'll give you this, and you need to do 4.4b. And then problem 3.4, which is pre-stress loss problem with all factors now, including the anchorage loss and the friction loss, right? So we haven't done that in this.
So we don't have the material. We didn't receive email. It's fine.
I know, that's what she was complaining also, and I meant to send this. At the end of the class, what I will try to do is, if you leave a few minutes early, and I'll send it over. That way I don't forget. Okay? So I'll send the pages, the handwritten examples, and I'll send also the overhead slides for PowerPoint. So you will be all right. And this is the other problem, 3.4105. This is based on the examples we have done in the class. And I'll send you those. Can that answer your question?
Thank you. I said
Yeah.
we didn't have it.
No, this is not. I may forget, so I thought I'll first go over this. I always keep my promises. I promised you I'll have assignments, so I have assignments.
Victor, is there a computer application for pre-stress concrete? Because there's lots of like very long equations that we are using.
You can write your own spreadsheet, really. There's nothing, nobody can stop you, because you input all these values that you're calculating. Really, that will be a good one. We can do that assignment maybe later on, right?
No, we can apply it for any assignment, but because
No, I'm not aware of
this. We have.
Barry might know something. Do you guys use anything for pre-stress?
Mm-hmm.
Yeah,
there's
there's
a Bentley product called the Leap Bridge Enterprise.
all right.
ComSpan and ComBox.
Is just for pre-stress concrete or anything else?
Yeah, just for pre-stress concrete.
Wow. But then this is not available here on campus, I thought.
It's expensive.
Yeah, okay. There you go. I did not know, so I had to tell you. And I knew he might know, so. There should be, it does make sense. Although it's not for rough calculations, the kind we do here for pre-stress loss, you can put it really in spreadsheet and calculate. You know. The selection of sections will be more complicated. Is that included in the software, Barry?
This is the what?
Selection of the girders, precast, pre-stress girders,
Yeah,
the bridge girders, yeah.
it's nice.
That gets more complicated.
But it's really complicated, and if you don't do this, then you won't know what it means.
Yeah. Oh yeah, of course. You don't want to. No. Here's my rule of thumb. As you've been in FEA class, is you don't just jump on a software and try to start using it. At least in the beginning, for at least 5 or 10 or 15 cycles, you do it by hand. Also, make sure you understand at least roughly, so that you don't get too far off and get totally wrong results. That is for sure. Okay. No, I was not aware. I thought there will be. Almost everything has a software these days, why not? But these are helpful only if you were to do, I will talk about that. If the department, our department can buy this, it won't be a bad idea really to go through that, and we can all learn, sure. I'm not in that business really, our company does, but not me personally. Okay, so I thought if someone could send me an email if I forget, but at the end of the class I'll do it. So let's go back and let's see, where are we in terms of PowerPoint? So, before we do that, let's see what were we doing last time. In chapter 3, we were doing chapter 3, set 2. I think we finished, but I want to make sure. So we were doing these this example on based on which, so let me fly over this here real quick. So this is simply supported pre-tension beam, lightweight steam cured double T beam. We went through that, I'm pretty sure. So let's go, so double T, and I'll send you this over again. And the same problem, and it was done in stages, and the same problem was done, solve this problem, assuming the beam is post-tension, right? And let me see if, make sure here. Post-tension, your assignment is post-tension, so this example will be a good one to follow, right? So we looked at that, I'm pretty sure. You can correct me if I'm thinking wrong. The only thing, like I was telling before, that friction loss is one thing we have to calculate differently than what we did in the previous assignment. And anchorage loss, where we need to know assume the anchorage seating loss is 1/4 of an inch. In your assignment, it is 3/8 of an inch, so you can follow the steps basically. Slippage is 1/4 inch here versus an assignment 3/8 of an inch. So accordingly, the strain will be different and the loss will be different. So let's see. So it is very similar. And we go through stage 1, which is transfer of 18 hours of pre-stressing. Right? In the assignment you got last one, I had asked you to do it in stages or step-by-step method. But we didn't tell what time is the pre-stress transfer is happening. So when I did the example in the class or the assignment in the class, I showed you can back calculate your timing based on the strength of concrete. Remember we had a formula that involves alpha and beta to calculate if you know the time, you can calculate the strength. If you know the 28-day strength, right? So you can calculate depending on the time. But if you can flip that expression, you can find the time if you know the strength. So that's what I did that would have been perfect if somebody had thought about that. But again, we didn't discuss in class, so no need to worry about if you did not do it, right? But otherwise, normally that's what happens. You are given a time. If you're not given, you can calculate the time, right? So anyway, 18 hours is given. So the first stage is where you're transferring the pre-stress force. So at that point, the friction loss and relaxation has already happened, right? And then in this case, stage 2 is where your topping is placed on top, this hatch line. So the topping is placed, so you're going to calculate all the losses again, right? Based on the stresses and gains depending on what's going on, right? So you are adding a 5,000 PSI gain. This one gains the pre-stress. Is that all making sense to everybody? That when I put this topping here, I'm actually increasing the pre-stress force. That makes sense to everybody? No?
No.
Okay, because we went through this, so let's see what's going on here. This is explained in the book also, textbook, but here it is. At the end of stage 2, the gain is, let's see, where did we calculate creep loss? Shrinkage. Oh yeah, in 3.8 we did calculate this. Stage 2, because our stages are still the same, right? Stage 2 transfer to addition of 2-inch concrete topping at 30 days. After 1 month of this casting, we put this top layer of concrete in the field. Because these are factory made, they assemble together, then you put the topping, right? So at that stage, we calculate the FCS, which is the stress in the concrete at the center of pre-stressed steel, right? So once you calculate that, then the additional stress is 519 PSI at the critical location. In this case, the critical location is not at the midspan, it is at 0.4 L, so we had all that discussed last time, right? So in that case, the moment is not WL square over 8, it is this little more complicated looking expression for moment calculation, right? Because we are calculating, this is the length of the member, this is the distance, which is L minus X is 28 versus X is 28, L minus X is 42. So that's what you need. Okay, so because our length is, I believe, 70 feet, right? The span. Let's go back here. Okay, so go back here, 70 feet, right? So 0.4 L will be 28 feet, right? That's what I had for X. So I thought you guys would pick up a little quickly. So anyway, what if you have a simply supported beam and you have uniform load, and I want to know at 0.4 L, if this is L, what my, or any distance X for that matter, then our expression is what I had showed you, which is Wx times L minus X and all that. So anyway,
We get it.
you get it, right? I didn't see enough heads nodding, so I wanted to make sure. Okay, so once you calculate the stress in the pre-stressing or concrete at center of pre-stressing steel, which is FCSD is 519 psi based on the same formula, which is moment divided by I multiplied by E. E being the distance from the neutral axis, right? So this is neutral axis, and this is E, right? So that's why we have E and I, and then relaxation and all that. Then you come down to this. Gain is right there. Increase in pre-stress due to overlay weight is the FCSD we calculated above, which is the stress in concrete due to this extra weight, or WSD or MSD, right? Multiplied by the N, which is the ratio of the elastic moduli, right? So you're trying to stretch the material on the bottom. When you stretch the material, by adding the load, it is going to have more tension. Does that make sense? So that's the gain in pre-stress. There is no, this is a gain, that's opposite to loss, right? So this gain has to be accounted for.
Excuse me. When you add the load, because stopping is loading, you're loading the elements. Now in loading, and we reducing the pre-stress instead.
We have lost, by 30 days, we have lost some pre-stress because of relaxation, because of anchorage,
Exactly.
and all that.
Exactly.
Yes.
But now when we add the topic on top of the element, and we reducing on that.
Just by adding? No, not because of adding.
Adding the
Before
load.
adding, we have lost.
Exactly.
We all know that, right? Before we added at 30 days this topic, we have already lost relaxation, friction, depending on what we are doing, right? All those things have creep, right? This thing has creep. This is under compression, so it's going to creep. That loss will happen. But when you add this, there is an increase also instantaneously as soon as you add the weight. As soon as you add the weight, you're going to create tension on the bottom, compression on the top, right? In concrete. So when you increase the tension on the concrete, there is a corresponding tension in the steel, because the two are bonded together, right? So if one is lengthening, the other one is also going to lengthen, stretch, pull, right? Does that make sense? No?
Yeah,
No.
I get it when you said stretch.
Yeah, stretch. Because we are stretching both materials together, right? You're stretching the concrete. In fact, if you keep on stretching, you will start having cracks, right? But before, we are not reaching that part yet. We are avoiding the cracking, right? By putting pre-compression. But you're losing, as you are stretching, you're losing. you're losing the compression. In fact, there is a thing called, I forget the exact word here, it will come here in chapter 4, where you make the stress at the center in concrete zero. In other words, it's not tension, it's not compression. It is a neutral point, right? And if you put further load, then the concrete is going to get into tension. But we have allowable values, right? 12 times square root of F prime sub C maybe, depending on what it is. You allow that much. But if you keep doing it, eventually the concrete is going to crack. Now, beyond that, your beam is going to behave like a reinforced concrete, right? Once you start cracking, then it's no more under compression, right? So that's the beginning of your end, not end really, but your reserve capacity is now coming into play. Your normal elastic behavior is loosening. You don't have full moment of inertia anymore. This is the full moment of inertia is from there to there. If you start cracking, the part that has cracked, suppose this concrete has cracked, there is more stress, tensile stress here than allowed, then your moment of inertia is now this much, right? So your moment of inertia is reducing. No more linear elastic behavior. Up to this point, till you have allowable stress here, then this concrete is behaving more like steel. It is not linear, but it is under compression. It will bounce back if you took off the load, except for creep, for example, right? Okay. All right, so I wanted to make sure this is not lost, right? So this is that. Then what we have done is this number, 5,048 PSI, is going to be the same for post-tension, more or less. So that's what we are doing. In post-tension calculation, we use the same number, although it will not be exactly same because in post-tensioning, there are different set of losses, right? So your pre-stress force is not same at 30 days. So it's kind of a rough calculation, but remember this 5048. So when you go to this example, then when you talk about end of stage 1 or 2, I think 2, you add simply this value of 5048, which is same as what you did in pre-tension, right? So you can arguably say that why could it be same? Because you have different set of, you didn't have in pre-tension, you didn't have friction loss, you didn't have anchorage loss, and yet you're calculating. Mathematically it is wrong, but engineering wise it is okay because it's close enough, right? Okay, that's the kind of calculations we're doing. I thought I'll let you know. So the next example we did go through, but this is very simple and I'll send you this. This one talks about calculating the change in pre-stress by lump sum method, by table 3.1, the ASHTO and all that, PCI. Really. So then we can find out that really the difference between what you have sweating through all this is only 5%. But this, well, keep in mind that this is disclosed only in normal conditions. If you are in a condition where the humidity is too high or too low, you may not get the same exact, right? Or you will get more differences. This is just a good example where things came very close. Good enough for many practical reasons. Okay. All right, so that takes care of that. So let's talk about, which I've been already talking kind of, chapter 4, right? So this is the end of what we need to discuss in chapter 3. Okay, so let's go back here. And I have put a bookmark here so I don't get lost. There it is. Start here on 240. No, that's all. Something is not right. I thought I was at 57. 360. Okay. I can take this off and we can continue. So let's see. Let's go over some theory here for about 10 minutes and then we'll have a break and then we'll come back. So I say slideshow and so we don't get. Okay. This is a lot of repetition here, but I think it will, just to summarize what we have been talking, we are transitioning from analyzing, and that was chapter 1, where we analyzed, we said, okay, find me the stresses. I'll give you the pre-stress force, I'll give you the properties of the section, and I'll give you the loads, and you tell me what the bottom stress and top stress will be by various methods, right? We discussed 2 or 3 different theories, right? And we found out that by no matter which theory you use, the results come out to be more or less same, right? What we are going to do now is change the discussion around selection. Like, now you're going to select the section so that the stresses are not exceeded. The allowable values are kept at every stage. Stage 1, 2, and 3, and that we will define what those stages are. Right? So item number 1 is, in pre-stress concrete design, the section is kept uncracked and concrete material is considered homogeneous and elastic. Uncracked up to service load. Beyond service load, if you keep applying overloading situation where you didn't anticipate, you put more load than you were calculating, then of course it will be cracked. But till that point, it is uncracked. And we assume this to be homogeneous, which is more or less true, and elastic. Now, elastic part, kind of assumption really, because we know creep is not elastic. So, for service loads, the pre-stress analysis is similar to that of a steel beam column. I had told you this before in class once or twice, that our member is really, we call it a beam, but really it is a beam column. Can somebody tell me why we call it beam column, not just beam? And why is it similar to steel beam column, the last 3 words? Why is it similar to steel, number 1? Why is it similar to beam that we all know, because it's a beam that we are analyzing? Why the word column? Anybody?
It takes axial load.
Yes.
Compression.
It's taking axial load from the beginning, right? So that's always there. We lose it 20% or so, but we are still always there. So this is not just a beam, it's a beam column, constantly, all the time, right? The other one is, and our column is not only axial load, but it is actually developing a bending moment opposite to what you expect, right? That's the whole idea of this, right? The steel, why do we use the word steel in this case? Because of the first item, which is the material is considered homogeneous and elastic. Concrete is not, but we keep it under compression so it behaves more elastically than otherwise, right? In a reinforced concrete, it is less elastic. In this case, it is closer to elastic, not exactly, but okay. The comparison to a steel beam column is more appropriate than that of the column or beam because of what we just discussed. It is advantageous to use a non-symmetrical flange section to efficiently use the concrete in compression, especially for simply supported case. So why we want to use non-symmetrical section? Like this is a non-symmetrical section, right? What's an example of a symmetrical section? That is a close to, if you don't put the slab on here, that's close to a symmetrical section. Symmetrical about this axis, about that axis. Here we have symmetry about this axis, but not about that. Right? So why is it done? Just, you all know this answer, because in concrete design, we use a T-beam more commonly if you want to be efficient, as opposed to a rectangular beam, right? Everybody remembers that? Yes? T-beam, neutral axis is usually in the slab. So what happens is that, okay, let's go back to that. Why is non-symmetrical section more efficient? Anybody wants to explain that? You guys are graduate students, so you might have heard that before, right? You remember hearing about this? That a non-symmetrical section such as this, like a T or double T, is more efficient than a symmetrical section like this in concrete design. Anybody remembers?
It's about the distribution of the compression and tension.
It has to do with that you're on the right track.
Because if you draw the distribution diagram,
Yeah.
you see when you compress, for example, beam, which is symmetrical, you will attain getting the neutral axis. You get it easier to the neutral axis when it is symmetrical than when it's not symmetrical.
Yeah, the neutral axis is, yeah, that's one point. You're on the right track. So in normal concrete, you design this kind of thing, like this is more efficient than a regular rectangular section with these bars. You can put these bars here. The reason being, which one is taking tension? This has tension, this has compression, right?
Yeah.
So if the neutral axis is here, which is typically what happens, then the concrete below the neutral axis is in tension. So whether it is there or not doesn't matter. All you care is were you able to put these rebars and connect it to this compression, right?
Yes.
So that's why carry all this weight? If I want to design a beam like this, I could, but I said this is useless right here. I don't need this because this part of concrete is in tension and cracked and not contributing to the behavior, right? So I simply say, okay, I'm going to do this because I have my rebars are here, and the compression. This is my compression area basically. If you calculate the neutral axis of this, it usually comes into the slab, right? So you do this. In pre-stressed concrete, we need, steel is stronger and concrete is weaker. So you need a whole lot of area in compression. So it is still efficient. This one is very drastic. This is not, in pre-stressed concrete, it's not as drastic because for service load, most of the section is in compression, right? Most of the section, except for the last part. So it is still contributing to some extent, but most of it is still on the top. Most of the compression is on the top. As you go down lower and lower, there's less and less contribution. So it is not that effective as regular reinforced concrete, but it is still better to have what we have seen in the example, which is the double T section. This is what is very common. If you go to the hotels and all, you will see this is not uncommon. If top of swimming pools, long spans, 80 feet wide and all, this is what you typically use. This is not that wide. There is slight taper. I got the example here. All right. So its advantages, you use non-symmetrical flange section. As stated earlier, the basic equation of chapter 1 are transposed. So remember, our equations are written as Ft equal to Pi over A and all that plus Md divided by Sx or something, right? Or you write the other way, Ix, and then this is E. Either way, right? So that's what we are doing. So what we want, we are after this Sx. This is what we want. We want to know how much of this we need if I want to not exceed this stress. I know this Ft is 0.45 F prime sub C, for example. I don't want to exceed this value. So if I know this, and I know all this, I want to calculate this. So that's what we will do. In your assignment, part 1 is how we flip these equations. One of them I have flipped, the other one I'll let you guys do, right? So this is that. The typical loading history is presented in figure 4.2 and 3. So let's look at that before we take a break, right? So what is the history in chapter 4? So just to refresh again one more time, we have seen these graphs. In fact, that was one of the quiz questions, right? So you have the rectangular cross section, just for simplicity. Normally you don't use rectangular section, but just to visualize more quickly. So that's your section. So these are various stages, right? The stage 1 is called initial pre-stress stage. So you just applied your force on the bottom half of your section. And so you have a permissible tension on the top, very small amount. and the maximum stress not to exceed, right, certain value, right? Depending on what strength you got at the pre-stress stage, right? This is 18 hours or 3 days or something, right? So this is that stage. Maximum stress in compression here and maximum tension on the top, which is both are within permissible limits. Then you go to C when you have self-weight and effective pre-stress. In other words, you have lost some pre-stress. As soon as you apply, you have lost relaxation, sitting and all that friction and everything has happened. And now you have added some self-weight, because when do you apply self-weight?
Self-weight.
Yeah. When do you apply it? What stage? Huh? Creep happens
Well,
throughout the life,
yeah.
of course. Self-weight applies immediately. As soon as you apply pre-stress, the brain cambers up because you're applying a moment, remember? You're applying a force on the bottom, so it cambers up, right? Instead of cambering down. Why is it cambering up? Because we are trying to prepare it to camber down and neutralize, right? There's a thing in steel design, in bridges, Barry must know this, that you put a girder with a camber, right? For the same reason that you're putting a camber so that when you put the load on the bridge, it will balance out and not sag as much because you're pre-cambering on the opposite direction. So we are doing the same thing, we are cambering up, and as soon as it cambers up, whether you like it or not, the self-weight is going to work down, right? So the self-weight comes on as soon as you apply the pre-stress force. Whether the beam is sitting on two supports or on a flat surface, it doesn't matter. Both cases, it will camber up and camber back down, right? Not all the way necessarily. It may not be flat yet. It may be still slightly cambered up, but not as much as you had started as soon as you applied, right? Anyway.
Is the degree of counteracting the camber that you put in when you're designing, is it considered like so much?
In which design?
I'm
Steel or
saying,
concrete? In here?
Yeah, I'm saying you're talking about cambering. Do you mind about the degree of cambering, and then the force or the load which is going to counteract that camber? Is it like
in steel? That's what we do. We find out a lot in steel design. We design a girder, steel girder. You find out how much deflection you expect for the service load, and you say, what is my sustained load? Typically, the dead load that I'm pretty sure will stay there. Under the dead load, I would like to have a flat or slightly cambered down, but not many times for longer span. What controls your cross section is the sag. You're supposed to have a sag of 360 L divided by 360 or 240, depending on what you use, live load, dead load, or both. So between L over 250 and L over 360 is how much you will allow it to sag. Typically, sometimes more, sometimes less, but that's typically rule of thumb. So you calculate and find out what is the actual displacement. Your stresses are good. The beam is not going to fail, but the sag is so much that it is not good. Your equipment is misaligned. If you want to have a flat equipment, it's no more flat, it's sitting like this, right? And you have ponding problem in the roof, water is collected, not draining where you want to drain. So you want to make sure that sag is not too much. So you calculate that sag for permanent load, and you put that camber or 75% of it. And then you allow, so that the total sag will now first come, dead load will flatten it out, and you put live load, it will go down, right? But that go down is much less than if you didn't have any camber, if you made a straight beam, right? So we are doing something similar here. Our beam, precast, pre-stress beam, pre-tension beam, is sitting on a floor. Remember that video we saw? So it was still, after applying the pre-stress, it still had a little camber up, right? That was because we still expect more to come and flatten and then sag down, right? So anyway, so this compression is less now, and there is a small amount of compression on the top. The tension is gone. That's not necessary. You may have zero stress on top if you apply the self-weight, or you may still have a slight tension. It all depends, right? It's all illustration. In other words, that's not a hard and fast. Then stage number D is where you're applying the full dead load plus effective pre-stress. So your pre-stress has gone down more, and you apply the topping, right? The dash line or whatever you're doing on top, some extra dead load. So that's when this one happens, where you have very small compression and a larger compression on top. See, the top compression keeps on increasing and the bottom compression keeps on decreasing till you reach this stage E, where you have full service load plus effective pre-stress. Full service loads means you have live load and dead load and all the loads you expect. And now you have a small amount of tension. The compression that you had is decreasing to the point where it is becoming tension. And what you had tension is increasing to the point where the top compression now could be close to what you will allow. What we read 0.45 times F prime sum C at the top, right? And the bottom will be what you will allow for tension. Beyond that, if you keep on applying loads, then you will, that's your parabola, the standard Whitney's parabola, right? That's what you have your stresses, right? And then that parabola is approximated to a rectangle and all that good stuff, right? So that in a nutshell is how our history will go. You know, in concrete, reinforced concrete, you don't talk about this, you just talk about this, right? So that's the difference. We are going through phases, right? Okay. 4.3 is a little more interesting. So 4.3 is talking about deflections, right? And combining these stress diagrams in different places. So you start out, and you camber up, and then as soon as you camber up, you apply a full dead load, and then flatten. Now this right here is where your deflection is actually negative of your cambering up. See, this is the deflection on this side. The deformation or deflection is positive or down. This is the up part on the left hand side. So this part, this right here, is this here, right? You're applying the pre-stress. And then somewhere, as you increase more and more load, you come to a point where you're all compression and uniform. If you are adding the load in a small fractions, that usually doesn't happen, right? Usually you are, from here you go to this, but this theoretically is possible if you keep on adding sacks of something one by one, right? So you could reach this point, and this is interesting. It's called decompression right here. This right here, where the CGS, the stress is 0. At the center of the pre-stressing steel, the compression in concrete or tension in concrete is 0, no stress, right? There is a thing called, this is the balanced part, where you're balancing the pre-stress load with the external load. Remember, that's the balance, remember the load balancing method? That's this one here. So the load balancing method. Beyond that, you will start tensioning to some extent, and then finally to the last part we saw here, right? And your deflection keeps on increasing. And then beyond that, you have this rupture, right? It breaks, right? So you see how we have to deal with all this, because at every stage, we want to make sure the tension and compression is not exceeded, right? Okay. Let me see if there is anything else here. So let's go back to, well, let's see now. This is a good time to take a break. My body is telling me maybe I should. Anybody has any question on the assignment? Or, yeah, assignment. Everybody's good? Okay. He was the most efficient, just one page.
Yeah.
If you had 2 pages, you had a perfect score. You just had to add one more.
Why?
You get perfect score.
I'm very environmental. Like, I don't want to waste.
You don't want to cut trees.
Yeah.
Okay. You had a question?
He's saving environment.
Because you know
只有2%。
That's why I had a question. You just started to answer a couple of questions.
Yes, because I don't like.
Oh, okay, yeah. So can I take it back?
上交。
Yeah.
什么？
你赶快去跟老师说一下，你都扣了没有？
I only have this. One point, but here is.
Lost in the fire.
Oh,
Yeah.
math problem, right?
Yes.
Okay, I got it.
And last time is also.
I'm targeting you, just kidding. I'm sorry. Thank you. No, I'm sorry. No, you did all right. I was looking at this. I said, I thought you had more. Oh, sorry.
Exam paper.
Yeah. Our exam is okay. I got all that. You gave me yours, Robert? Thank you.
Yeah.
It's so cold.
Yeah, it is cool. It is true. I don't know why. The thermostat, okay, yeah. I don't want to put to 78 like last time. Somebody has put this at set to 60 degrees.